In this video, we're going to give you an introduction to some of the concepts involved when you get to the 3D modelling side of the Aspire program. Firstly, let's think about how we represent the 3D data. Essentially, what you're looking at when you look at an Aspire model is a grid of points, each one of which is at a different Z height. The concept is essentially the same as these executive toys where we have the pins and you can push a 3D shape into them and see that represented by the different heights of the pins being pushed up. The difference in Aspire though is we're using 1 million or more points, so we can represent a much more complex and smooth form, and we don't really see each individual location. In the software, you'll typically see these points referred to as pixels. This is the same terminology that you may have heard used when people describe the points or dots that make up a 2D computer image. And really it's a very similar concept in terms of the more dots you have, the better quality model or image that you'll have. The quality setting in the software is referred to as the resolution. You define this when you start a new job under the job setup. The section in the job setup form for modelling resolution is highlighted with the red rectangle you can see on the screen here. By default, you're presented with 3 options for this. Standard resolution means that you'll have 1 million pixels, high resolution means your model is represented by 2 million pixels, and very high resolution means that you'll have 4 million pixels over the surface of your entire work area. So this presents a trade-off really, because higher settings give you a better quality model but will mean longer calculation times for some modelling operations and for some toolpathing. So really it's just a case of balancing those things out so that you get something that's appropriate for the type of work you're doing and the computer hardware you're running. It's important to note that if your job only has 2D or 2.5D content, so essentially if you're working with vectors and you're toolpathing those vectors and your part doesn't have any 3D component in it, then the resolution will have no effect on the quality at all. That's going to be all down to the quality of the vectors that you've drawn and the settings you use in the toolpaths. There's detailed information on the resolution and the specific technical information behind it on the FAQ section of the support.vectric.com website. So if you want to learn more about it, visit the website there, go to the FAQ section and search for resolution, and you'll find a very detailed PDF document that describes exactly the effect that this has on the 3D model in the software. For people that are new to this concept, it can be quite abstract and difficult to understand. So rather than rely on the fact that you grasp this completely, let's look at a few simple rules that will help you get good results even if you don't totally understand the technical aspect of it. So some rules for success. First, you want to maximize the area of the job that the 3D part covers. So you don't want to have lots of space in your job that is irrelevant to what you're actually machining. So typically what you're going to do is make the job size slightly bigger than the part you actually plan to toolpath. And the reason it's got to be slightly larger is you need to leave a bit of a border in case you want room to do things like a cutout toolpath or to have position to clamp things down. So here you can see we've got a 3D model of a horse and the rectangle around that represents the job setup. What you don't want to do is make your job size the size of your table or your material unless that's the size of the part you're cutting. So here if we look at the example we've got at the top, we've got a 10-inch horse's head, so this is 10 inches across, and you can see in the first version of this we've set up a job that's just slightly bigger than that, maybe 12 inches in width. At the bottom we've taken that same 10-inch horse, but now we've placed it in a job size which is 4 feet by 8 feet. And if you look to the right, you can see the quality difference that makes. At the top, we've got a very high quality image because we're maximizing the number of these points or pixels within the work area so that the model can use those to get the definition. At the bottom, we're getting much fewer of those points under our model, and so you can see the sacrifice in quality that we're going to make if we do that. So very important. Maximize the area of the job that the 3D part covers. Good rule of thumb for this is to look at the part you plan to toolpath and then just maybe add an inch or a couple of centimeters if you're working in metric around that, assuming that's large enough to accommodate any kind of cutout operation that you're going to do. In some situations, you may need to rotate the part to best fit it into your work area in order to maximize the number of pixels that are being used. So that's just something else that you may want to think about if it appears that there's a lot of white space in your design which is not being cut. So once we've got our part set up, what is it that actually tells the software to push these pixels up to the different Z heights? Basically, we use a concept called components. Components are the word that we use to refer to the 3D objects in the software. So when we create these components, that's going to push up the pixel heights in the software, and then by combining these together is how we get the overall finished 3D object. We manage these components in something called the component tree that you'll find on the Modeling tab. So let's take a look at an image of the Modeling tab, and there we can see at the bottom, highlighted with the red rectangle here, the component tree, and you can see underneath there's a list of components, and each of those is on what we refer to as a level. Now the result of all these individual objects combining together is what gives us something that we refer to as the composite model, and this is essentially what you see in the 3D view. The result of all these components and the combine mode, so how they're interacting with each other, is what gives us that finished part, and that's what we're going to machine when we go ahead and use 3D toolpaths like the roughing and finishing. Now that model could be just a single component on a level, or as you can see here, it could be an assembly of many components and groups on levels which are combining. The result of this, as I say, is what you see in the 3D view. Again, it's very important to reiterate that the combination of all these things acting together gives us that 3D object, and that's the thing that we're going to machine. So how do we generate these components? Basically, there are a couple of different ways to do this. We can use the modeling tools in Aspire, so we can take a vector, for instance, and we might go ahead and use something like the Create Shape tool to build that into a dome, or we might use things like the 2-rail sweep or the extrude and weave in order to create a swept shape. We also have the ability to do sculpting, so we can interactively work with the 3D object as if it was a sort of virtual piece of clay. Another option we have is to take an image and to create a model from that, so to generate some kind of a texture, and that's one of the ways that we create the lithophanes that you may have seen. An alternative to building the shapes from 2D data in the software is to go ahead and import an existing 3D model. This may be something that you've previously made in Aspire and saved out. It may be a piece of 3D clip art that you've purchased or downloaded from the internet, or it may be a 3D model that you've created in another CAD software program. There are many different software programs available that can create a 3D object, and ultimately you might want to bring those into Aspire in order to maybe finish edit it, combine it with other objects, and then eventually create toolpaths on it so that you can cut it on your CNC. By working through the other modeling tutorials, you'll learn how to use each of these functions, how to use the 3D editing options, and also how to import and work with data that's been created from external sources as well. Now, when you're creating a job, what's the typical 3D workflow? To start with, as with any job, 2D or 3D, you're going to define your job concept and assemble reference material, and that may be information and parameters from your customer, or it may just be things that you bring together yourself in order to start to build your design. Next, you're going to create good quality vectors. All 3D work, if you're using the modeling tools in the software, is going to benefit by making really good quality vectors. So everything you learn and know about drawing in the software is going to help you even when you get to the 3D, because the better the vectors are, the better your 3D shapes will be. Next, you'll use those vectors and the modelling tools to build basic shapes and start combining those together, maybe into what we typically refer to as sub-assemblies. So this is where you start to use the levels and groups in order to combine individual shapes together to slowly build a more and more complex shape, and that's managed in the component tree. As you're doing this, you may use some of the editing tools to start to smooth and blend and get the shapes to interact in just the way you want. Next, as with any project, you're going to iterate through, so you may get to a stage where you need to go back and make changes to something you did earlier based on information that you found out later on in the process. Eventually you'll get something that's very close to being the part you want to machine, and then you may just do some final finishing, so there may be some last minute sculpting or smoothing in order to get the quality or blend of the objects. You may need to create a vector border, basically everything you need to get ready to go over and start creating the 3D toolpaths. The most common approach to machining a 3D object in the software is to use two types of toolpaths. You're going to start with what we refer to as 3D roughing, and this is used to remove the majority of the material around the part. So typically it uses a larger tool, fairly loose settings for that tool so that we're taking a lot of material on each cut, and also we're going to keep that slightly away from our finished object as well to make sure that we've got some material left for the second type of toolpath, which is the 3D finishing. This is going to use a smaller tool so that we can get the detail, and it's going to use a very small step over, and that's the distance between each pass the tool makes. The image you can see on the top right here shows the toolpath, shows the individual lines of that toolpath, and the image at the bottom there shows the typical result we get at the end of that. The smaller that step over, the better quality the finish will be, but of course the penalty is the longer it takes to cut. Now, as well as doing purely 3D toolpaths, you might combine those with 2D and 2.5D toolpaths. For instance, in this case, we've gone ahead and done a 2D profile toolpath in order to cut the part out when we've finished. Some of these toolpaths could also be projected onto a 3D shape as well. For instance, you may want to engrave text onto a banner or something like that, in which case you'd do your 3D toolpaths first, then you may do something like a V-carving on the text, and there's a checkbox in the toolpath there that says project that onto the 3D model, and that will then just follow the contours of the 3D model with the parameters of the toolpath you've set up. In addition to creating a 3D object to output to the CNC, you may also want to export the 3D model when you've finished. This may be to take it into another CAD program. It may be to export it to a 3D printer, so save it as a mesh so that you can 3D print it. It's also possible to export the 3D object as a 2D grayscale, and that's something that can be used in other software and also to power a laser. Some lasers have the ability to cut a grayscale as a sort of dimensional object. So that concludes this quick overview of the general concepts behind the modelling in Aspire and the typical sort of workflow we're going to use with it. Now, if you're interested in doing this type of work, we'd recommend that you watch all the other modelling videos and the tutorials that cover the 3D machining. Thanks for watching.